Good afternoon, everybody. Welcome to Check 2020. My name is Kelley. I'm from Emporia State University. Today's session is KState's Journey to Cloud Architecture by Zoglmann from State University. If you have any questions, please hit the Submit a Question button on the page for this session. And with that, Kurt, I'll let you take it away.
Well, hello, everyone. I'm Zoglmann from State University. I'm an applications architect, and I've been with KState coming up on 20 years. Kind of hard to imagine. So I've seen a lot of change, and I've primarily worked as a software developer and increasingly playing a role in our architecture moving forward. I'll go ahead and share my presentation. I have to re-find it again. The curse of too many windows. So I'm just going to briefly cover computing at KState. We have actually a pretty long history, and we've gone through a lot of change over that period of time. And then we'll go ahead and talk about some of the specific architectural and operational changes that we've had to make moving to the cloud. I have quite a few slides, so I'll try to go quickly to make sure I don't go over time. I've given this presentation once before, and we finished on the dot. So I will try my best not to linger. And skip over that. So this is a quote, I guess it comes from me, but to understand where we are going, it's really helpful to know where we've come from, primarily to have that context. It's pretty hard to predict the future or have some insight into where we're going unless we know the broad brushstrokes of where we've come from. I really like analogies. They help quickly and easily help people understand a complex subject. But the caveat is that analogies are great until they're not. If you push them too far, they break down. And when thinking about the eras of computing, if we think about how we treated those computing resources, initially, if you're familiar with Lord of the Rings, you know that it's precious, my precious. Our mainframe computers were vastly expensive. They were coveted. Oftentimes, access was limited. And we transitioned into an era where we had multiple smaller computers, typically in a data center, and we named them. They were our pets, and we cherished them, especially if you were a system administrator or someone who helped maintain those systems. But then as we move into the era of the cloud, everything's disposable. And, we don't name them. We can easily spin something up new. We try to codify everything so that way it can happen quickly. And then we're just entering an era where things are ultra disposable. The resources are highly divided. And so we're really talking about containers. So I call this the insect swarm. And if you think about where we're moving to, it's hard to predict the future, but we know that quantum computers are going to play some role in our computing future. The question is, what will it be? And will we see somewhat of a repeat? We know that quantum computers are very expensive. Just maintaining the very low temperatures may make it hard to see them distributed across campus. So anyway, so KState, I wish you were here live. I just have two quick questions. So what year did KState get its first computer? Think about just even decades. Are we talking the 1940s, 1950s, 1960s? pause for a moment, get a number. So it turns out it's actually 1958. So we got started pretty early on. Um, and you might think to yourself, well, what kind of computer was this? Um, Obviously, it's some type of mainframe. You probably would be hard pressed to guess the exact model, but you could probably guess that it was an IBM mainframe. So KState's first computer was an IBM 650. And last semester, I took an interest in looking at lower level architecture, microcontrollers down at the hardware level. And so I thought this was really fascinating. Um, so this is a picture of the IBM 650. The picture in the lower right-hand corner is actually a picture from K-State, but I couldn't find a high-resolution picture. So the bigger picture is from Texas A&M, but it gives you some idea of just how big these machines were. And it's even more interesting taking a look at the insides of the IBM 650. If you look right in this area, these are vacuum tubes. They require a huge amount of power. If you look at the transformers, you can see this was not something that you could ever run on batteries realistically. And amazingly, hopefully you can see my mouse cursor, this was the main memory. And memory in this case was more like a hard drive. So there was a steel drum that spun very quickly. And these were read-write, we call them heads. So you can imagine that access to memory was much, much slower than we would typically expect in today's computers. And some quick trivia about this machine. So if you're familiar with Kansas State University's campus, it was located in Seton Hall, which is on the south side. This thing weighed a lot. It weighed 5,400 pounds. And as I mentioned earlier, it took a lot of power to run these vacuum tubes, 22 kVA to supply the power. The power supply alone weighed 3,972 pounds. These were big transformer-based power supplies. Modern computers increasingly make use of switching power supply modes. As it kind of sounds like, you might infer that it's based around transistors, and it just requires a lot less power. So think about that spinning drum. Keep in mind that the operator sat right in front of that. That thing spun at 12,500 RPM. If you've been around a while, CDs are kind of going out the way of the dodo. But remember those souped up CD-ROM drives? Man, when they spun up, it just sounded like they would shatter. And in fact, when they topped out around 80x, occasionally they would shatter. And you could just imagine thinking about that steel drum potentially shattering. But as I mentioned earlier, because this was memory, it took 2.5 milliseconds to access any particular byte. And this thing had very, very little amount of available memory, somewhere between 1,000 and 4,000 words of memory. I'm not entirely sure how much our specific mainframe had. This would be equivalent in today's architecture between 4.2 to 17 kilobytes. And in terms of programming languages, what's fascinating to me is that even at this early time, there were a number of programming languages that were available. Even just moving to assembler at this time was a major leap forward. If you've ever taken an opportunity to try to learn assembler, try writing direct machine code. It's possible on the TI-82 calculator if you have it. It's a wonderful exercise just to understand how far we have come, especially if you're a software developer. And I tried to look up what on earth this programming language called Spaces. It's supposedly a business-oriented language. I'm guessing it was some type of precursor to COBOL. Not sure. So what's interesting too is that some of our language around computing has changed. So in the 1950s, a computer referred to people who calculated. And what's interesting is that the era of computers was more transitory than a lot of people realize, moving from IBM tabulators to a general purpose computer was very stepstone like. It wasn't just a major, oh, here's a new thing, a general purpose computer. There are many incremental steps along the way. But what's kind of interesting in researching the IBM 650, it was advertised to fit in a room and it was user friendly. Yeah. We have completely different notions of what it means to be user friendly. And when you think about uptime, especially in the cloud, think about durability numbers. If you've looked at Amazon, AWS, Azure, and these others, usually they're talking about 9 nines or 11 nines worth of durability or availability. But no, you were lucky to have about 80% uptime with this particular computer. And you had to fix it yourself. You had to have parts on hand. And this thing was very, very expensive. It was available in 2019 dollars at around $28,000 a month. That is amazing. And one of the reasons why the IBM machines took off over some of the competitors was because they literally had blinking lights to tell you that it wasn't stuck in some type of infinite loop. And if you've ever tried to write machine code, it's so easy to make a mistake and to have the whole machine crash. So the next generation of machine was really based around core memory. As we transition to more modern mainframes, this is an area I'm personally not as familiar with, but we really had a powerful system with the IBM 3084Q mainframe, which was installed in November 1989. You can see this pictured over here, then bringing it into Hell Library. And then we begin this very, very long transition from the IBM mainframe to Sun SPARC. We had the Laser project, which allowed us to retire the mainframe to get away from the mainframe-based student financial systems. But eventually, the mainframe was decommissioned in 2009, not without a tremendous amount of expense. A lot of man hours were put into that project. And then we began to move from expensive servers, Spark-based, to more commodity Intel-based servers. And the number of physical servers in our data center really began to skyrocket into the hundreds. And then around the middle 2000s, we began to dip our toe into VMs, which gave us a lot more flexibility and gave us some more options as far as life cycle of the hardware. But as many of you probably are aware of, we certainly are painfully aware of, I thought this was a quite appropriate picture of our pets looking down at us as if they were looking down at someone who had died. That's certainly what it felt like. So a couple years ago, I was at the Czech conference, and it was so hard to be away while we were trying to get our identity management system up. This is just a handful of publicly available pictures from all the damage that was done to the inside of our library. It's just heartbreaking. But with every tragedy, there's a lot of opportunity to move forward, to do something new. And it's hard to speak for everyone within K-State IT, but I think we have all embraced the opportunity to move to the cloud. And so we're moving away from pets where we name them Darth Vader, whatever, to disposable resources, unnamed resources in the cloud. The one thing that is a little difficult getting started in the cloud, if you haven't taken a look at it, is just how many options there are for absolutely everything, every type of component. Whether you're talking about databases or which languages that you write your application in, what continuous integration and continuous deployment options, what kinds of platforms that you use. Oh, and by the way, this is a couple years old, intentionally. The most recent image, you couldn't even make out any of the icons here. So it hasn't gotten any easier. Moving forward, there are many, many options at every level. So it's both a good thing, but it can be a little overwhelming on where to get started. So when we talk about architecture, we want to lean towards being cloud agnostic. That will give us some future flexibility, but we want to provide enough guidance so it's not a complete Wild West. And what we learned with AWS's help, they have the AWS well-architected framework that covers both architecture and operations. And it is our default choice for how we architect in the cloud. It's cloud agnostic and it's exceptionally comprehensive. And AWS is renowned not just for being the 800-pound gorilla, but being the most mature, both in terms of implementation, mindset, and just forward looking. The AWS well-architected framework could be a very long presentation going into each one of these pillars. I can provide a link to this, or you can Google it, find their white paper on it. So K-State has been operating in the cloud for about a year with a lot of seriousness, a lot of investment. And I would say that we have focused most of our attention on just three of these pillars. Operational excellence, which includes codifying all the infrastructure, security from the get-go. We want to make sure that we set things up correctly. And as we create new accounts, that we ensure we're following all the best practices and following all of the decisions that we've previously made around security. And then cost optimization. As you begin to bring more resources to the cloud, it becomes increasingly important to focus on being frugal, reducing your operating expenses as much as possible as you move from a CapEx, capital expenditure and planning, to an OpEx, operational expenses. And both myself and several other people who have put a lot of focus in this particular area over the last 4 or 5 months, we probably are saving K-State on the order of around $10,000 per month. We've made dozens of optimizations. I could certainly spend an entire talk going over that, but don't have time necessarily for that. These are the links that I alluded to. I hope if you're interested in this topic that you check this out. You can easily find these links if you just Google it. And one thing I'll point out is that AWS has an excellent training portal. All their training is free, at least the online stuff. It's just an excellent resource. So when KState got the green light from leadership to move to the cloud, to have a cloud-first strategy, we partnered with AWS in this AWS Migration Readiness and Planning, or MRP project that's spanned approximately 6 months. And it focused on several areas. One is the business case. If leadership and others are not fully invested in this move to a OpEx model, you're going to likely fail. The other thing that I think was surprising to us was just how much preparation and work there is to prepare people to operate in the cloud. It's not just a matter of sending people in for training. Training is part of it. Part of it is getting the organization to adopt the right kind of mindset to be efficient and effective operating in the cloud. Security, highly suggest that you partner with AWS or other partners to accelerate making wise and good decisions as you, for instance, set up your landing zone. The other part is operations. So as a part of our AWS Migration Readiness and Planning project, we initially chose 5 applications to migrate, and ultimately we ended up collapsing this down to just focusing on one application, which is highlighted here, our undergraduate admissions application. And this application is a homegrown system that we have had around probably for at least 10 years or more. I guess that slide isn't a detail on this application. So the admissions application is written in Java. We have a web application container that it runs in. It was JBoss, but now they've transitioned to calling it Wildfly. And there's just a lot of different layered components that's a part of this application. And it was not easy initially to figure out how to make this a cloud native application. So this wasn't going to be just a lift and shift, which would be an easier way to dip our toes in, but we really wanted to understand more fully and deeply how to move applications to the cloud and to be able to both reduce the expense of operating and to be more efficient in those in how we operate. I won't spend a ton of time on this slide other than just to mention that it is a big, big deal to leadership and others. There's just a lot of changes. The biggest one is instead of planning years, oftentimes in advance, that you're going to need to purchase some big, expensive set of machines or hardware, to instead budgeting on a per month basis in the current month or for the year. And it just takes commitment from leadership and others to make this change. So when we initially started looking at making our undergraduate admissions application cloud native, we wanted, from a security standpoint, we wanted to limit the blast radius in case there was some type of compromise. So for instance, if Apache was compromised, we wanted to make sure that the application server itself wasn't compromised. So we had to think about making sure that there was security at all layers. And then there were some specific transitions that we had to figure out. So in the past, we had been using the F5 as a load balancer and firewall, and we needed to shift to a application load balancer, which is it's just a service that AWS provides. And then we wanted to move from our own managed Oracle instances, Oracle RAC, to using Oracle RDS. And we wanted to have everything isolated, but we didn't want to increase the cost or the complexity. So these two things tend to play out against each other. And we wanted to ensure that we structure things in a way that would allow us to continue to evolve the application over time in such a way that we didn't lock ourselves in. So talking about security, this is one area where no matter how much we value security, physical security, we cannot compete at all compared to what AWS has in place to ensure physical security. So this picture over here on the right, this is not our data center, I promise, but this is just an example of how simple oversight can lead to some type of vulnerability or loss of hardware or data. Someone decided to put drywall over a window. Not very secure. It's interesting if you're interested in cloud security. I recommend Googling around for just some of the descriptions and the controls that AWS and other cloud providers put in place. But I'm not going to read all this. It's very extensive and far more than any of the state institutions has the resources to manage. So on the topic of security, we moved from an era where there was limited amount of controls and technology to just a plethora of options available to us. So we moved from an era in our own data center. This is not physical security, but just using SSH, VPN, firewalling, either host-based and on the F5. In the case of admissions, it was both, to making use of all kinds of technologies to secure the application. So one of the things that makes our security personnel smile is the fact that we're now encrypting all of our data at rest and in transit. And so we're using things like KMS, Cloud HSM, and then there's even, admissions doesn't use it, but there's even support for encryption in all of their native services, like S3 allows you to encrypt both at rest and in transit. The other cool thing is that AWS provides active monitoring and response to DDoS on your behalf. Other things like web application firewalls, that's something that was on our radar, but we're actually moving forward with implementing this. There's some caveats. You do want to do some testing ahead of time, or it may break. For instance, we've had some recent issues with SOAP requests getting intercepted. So it's not something you just turn on. It's not the easy button, or it's not likely to be the easy button. And there's a little bit of additional cost too, and using WAFs. We're also using things like VPCs, routing tables, on and on. Not going to read all this stuff. The other big change was maturing our ability to codify everything. And so really moving to the next level of codifying our infrastructure. So previously we were using Chef and Vagrant to codify the server configuration, but we can go much further on the cloud now. Since we are primarily adopting AWS, we're using CloudFormation, which I can show you here in just a second. And what else do I want to say about this? Nothing. I guess I can show it to you now. Which window is it? So all of our stuff is checked into Git. And this particular repository, the AWS KSU admissions CloudFormation, is exactly what it sounds like. This is what codifies how all the EC2 instances or virtual machines, how they're configured. And this is kind of what it looks like. This part of the script is not that interesting. It just prompts you for different parameters. And so in AWS, one of the cool things that you can do is you can enable less technical people, or maybe you just want to control within an account what people can spin up, only authorized, configured types of things. So in our production account, there's an entry for admissions. So if we're going to deploy a new version, someone with the right credentials and access could come in here. And it's a matter of simply specifying which version that you want to launch into the production environment. And then, as you kind of seen in the script, very, very briefly, there's a bunch of parameters and other stuff you have to specify. So then you would click next, and it would begin spinning all this stuff up, all of the networking, all of the security controls, just everything. And what would normally take us calendar time, probably a couple of weeks at best, to have all the different people who would normally set things up in our data center, this now just takes 10 minutes or so. So it's much, much faster once all the infrastructure is configured, and it makes it easier to know whether something's out of compliance in terms of, did someone make a manual change? Ideally, we want everything to go through a software development process of review, testing, and then a release into production. So the networking also significantly changed. So on-prem, we're primarily making use of static IPs. The other thing that for our applications, we really needed to make use of multicast and or broadcast. So there's many protocols where they'll rely on one of these two mechanisms for cluster members to find each other. That's a problem in the cloud. In the cloud, whether you're talking AWS, Azure, or others, there's no multicast or broadcast support. There's a really good reason for that, but I'm not going to get into that. It is technically possible to work around this with an overlay network, but it's not very efficient, and I don't recommend it. If you can, whoa, what's going on? And I don't recommend it if you if you can possibly move away from multicast and broadcast. In the case of admissions, it's a Java Wildfly-based application. We needed to change the way that discovery mechanism works. And so there were two pieces to it. One was JGroups, the other was mod cluster. You probably don't want to know about this unless you're doing this kind of application development, so I'll skip it. Many of you have probably already seen something very similar here. As you move from on-prem to a more managed service, more and more pieces or components are managed for you. And oftentimes that's the way you want to go. So when you're thinking about a cloud first strategy, you want to move as as much as you can to the right for whatever it is that you're transitioning to. So the emissions application itself, this is what it looks like. We have the WAF setting here in front in the VPC. And then we have an application load balancer that straddles two different AZs. Availability zones are really different data centers that are near each other physically. So latency is not an issue, but they're far enough apart that if disaster strikes, it's unlikely to take out both. So then we have some very small EC2 instances or VMs. These two right here, these are running Apache. And then these that say C5, we're really not using C5s. These are what's running the web application server and providing the function of the application. And then we have our database here. And then there's some external databases. Kind of running out of time. The other thing to think about as you're architecting for the cloud is thinking about how you want to set up and provision, maintain permissions across different use cases. So thinking about like a sandbox where it's more permissive, people can set things up to play around with, to understand, prototype, and then, well, there's just lots of different use cases. So for testing, running in production, some type of shared account. I'm going to skip this. And this is what it looks like running here. Essentially what's going on, KState hasn't moved all of its DNS up to the cloud. So Route 53 is what's controlling DNS for this application. There's essentially, we're putting a CNAME in our DNS to point to the application load balancer's certificate name. So can't go into a lot of detail. We're already wanting to make a number of future changes to make it cheaper to operate, consume less resources, and just give us some better flexibility. And so this is really moving into the area of containers. We haven't fully decided on what type of orchestration engine that we use, whether it's ECS, Fargate, Kubernetes. There are just lots of options. Same thing for software-defined networking, what type of overlay network that we use. And then we want to, as much as possible, continue to mature our CI/CD pipeline, also known as continuous integration, continuous deployment pipeline, so that way anytime you make a change within our repository, we go ahead and fork out the appropriate build and let you know as soon as possible if something failed. So I think I finished just about 5 minutes early. So if there's any questions, I am open to take them.
It, if I'm looking at this correctly, it doesn't look like we have any questions currently, but if you want, we can give it just a minute or two, see if anybody has any questions.
It was kind of a whirlwind tour.
Hey Sam, can you just confirm for me that you're not are you seeing any questions in there? Okay, thank you. do you have any final remarks or anything you'd like to tell our viewers, Kurt?
Um, sure. So if you're curious about the background, this is actually from out on the Konza Prairie Trail. So if you ever have an opportunity to visit our campus, I encourage you to take a hike. It's just a few miles outside of town. Your choice of either 2, 4, or 6 mile loops is spectacular. About 1 or 2 weeks after they burn in the springtime. So encourage you to visit sometime.
Sounds great. Well, since we don't have any more questions, we can probably close out just a few minutes early here.
Sure.
So I just want to say thank you, Kurt, for your presentation, and thank you for everyone that's come and been a part of Check 2020 today. And we'll hopefully see you tomorrow.
Thank you.
Mm-hmm.